Welcome to Spring LIB.
This is the answer to Chapter 11, problem number 47 from the Smith Organic Chemistry textbook. And this problem says, what reactions are needed to convert alcohol A into either alkyne B or alkyne C? And so looking at alkyne B and alkyne C, what we should notice is that the only difference between these two molecules is the configuration of the stereocenter. So in B, we have the deuterium on a wedge and the hydrogen on a dash. And in C, we have the opposite configuration. And so looking at A, we have the hydrogen on the wedge and the deuterium on the dash. So A and C have the same configuration at that stereo center, and A and B have opposite configurations at that stereo center. And so we're starting from an alcohol and we need to go to an alkyne. There are different ways that we can do that. And so basically, to keep that stereo center with the same configuration, so to get to C from A, we're going to have to invert twice. So we don't have access to reactions that will just leave that stereo center alone. So we're going to invert it and then invert it a second time to get back to its original configuration. And to get from A to B, we'll actually use a reaction that's going to retain the stereochemistry, retain the configuration at that stereo center, and then we'll use a second reaction that will invert the configuration, and that will get us that inverted configuration in the final product. And so let's handle going from A to B first. So both of these are A. Let me just label them. Okay, and so to go from A to B, the first thing that we're going to do is we're going to tosylate this alcohol. So we'll use tosyl chloride and some pyridine as the base, and that is going to tosylate this alcohol. And so instead of OH, we will have OTS. And the important thing about this reaction, the reason that I selected it here, is that is going to retain our configuration at that stereo center. So we have retention of the original stereochemistry there. And so now our next reaction is going to be to use an acetylide ion. So there's our acetylide ion, and that's going to do an SN2 nucleophilic attack at that carbon, that is the stereo center. And because it's an SN2, we'll get inversion of chemistry, of stereochemistry. Geez. Okay, so inversion of stereochemistry. So here we've added our alkyne, and we've inverted our stereochemistry at this carbon. And so now we have the deuterium on the wedge and the hydrogen on the dash, and that's the configuration that we need for B. And so that's B. So then to go from A to C, as I said, we'll take advantage of the exact same process, but with a different first reagent that's going to invert our stereochemistry. And so if we use PBr3 here, PBr3 is going to also proceed through an SN2 mechanism. And so the product from this PBr3 reaction is going to be the alkyl bromide, but our stereochemistry here will be inverted. And so this is good because now when we use that same acetylide ion as we used in the first part of this problem, we will again get inversion of stereochemistry. And so our stereochemistry will be back to the configuration that we had in A, in our starting material. So there's our alkyne that we've added. And then here is the stereochemistry, which has been inverted again. to give us that original configuration. Okay, and so that's the answer to this problem. And the way to approach it is just to think about what you have to do to end up with those different configurations at that stereo center, and then select reagents that are going to invert or retain that configuration. And that's the answer to chapter 11, problem number 46.